microservices. And now let's go ahead and let's dig in on the challenges that we've encountered over the last 7 years and some of the solutions and philosophies behind that. So I love junk food, and I love this image because I think in many cases the problems and solutions have to do with the habits that we have and how we approach microservices. And so the goal is to get us to eat more vegetables in many cases. We're going to break this down into 4 sort of primary areas that we're going to investigate. There are 4 dimensions in terms of how we address these challenges: dependency, scale, variance within your architecture, and how you introduce change. We're going to start with dependencies, and I'm going to break this down into 4 use cases within dependencies. Intra-service requests. This is the call from microservice A to microservice B in order to fulfill some larger request. And just as we were talking about earlier with the nerve cells and the conduction, everything's great when it's all working, but when it's challenging, it can feel like you're crossing a vast chasm. In the case of a service, calling another service, you've just taken on a huge risk by just going off process and off your box. You could run into network latency and congestion. You could have hardware failures that prevent routing of your traffic. Or the service you're calling might be in bad shape. It might have had a bad deployment and have some kind of logical bugs, or it might not be properly scaled. And so it can simply fail or be very slow, and you might end up timing out when you call it. The disaster scenario, and we've seen this more than I'd like to admit, is the scenario where you've got one service that fails. With improper defenses against that one service failing, it can cascade and take down your entire service for your members. And God forbid you deployed that bad change out to multiple regions if you have a multi-region strategy, because now you've really just got no place to go to recover. You just have to fix the problem in place. So to deal with this, Netflix created Hystrix, which has a few really nice properties. It's got a structured way for handling timeouts and retries. It has this concept of a fallback. So if I can't call service B, can I return some static response or something that will allow the customer to continue using the product instead of simply getting an error? And then the other big benefit of Hystrix is isolated thread pools and this concept of circuits. If I keep hammering away at service B and it just keeps failing, maybe I should stop calling it and fail fast, return that fallback, and wait for it to recover. So this has been a great innovation for Netflix. It's been used quite broadly. But the fundamental question comes in. Now I've got all my Hystrix settings in place, and I think I've got it all right. But how do you really know if it's going to work? And especially, how do you know it's going to work at scale? The best way to do this, going back to our biology theme, is inoculation, where you might take a dead version of a virus and inject it to develop the antibodies to defend against the live version. And likewise, fault injection in production accomplishes the same thing. And Netflix created FIT, the fault injection test framework, in order to do this. You can do synthetic transactions, which are overridden basically at the account or the device level. Or you can actually do a percentage of live traffic. So once you've determined that everything works functionally, now you want to put it under load and see what happens with real customers. And of course, you want to be able to test it no matter how you call that service. Whether you call it directly, whether you call it indirectly, you want to make sure that your requests are decorated with the right context so that you can fail it universally, just as if the service was really down in production without actually taking it down. So this is all great. This is sort of a point-to-point perspective. But imagine now that you've got 100 microservices, and each one of those might have a dependency on other services or multiple other services. There's a big challenge about how do you constrain the scope of the testing that you need to do so that you're not testing millions of permutations of services calling each other. This is even more important when you think about it from an availability perspective. Imagine you've only got 10 services in your entire microservice infrastructure, and each one of them is up for 4 nines of availability. That gives you 53 minutes a year that that service can be down. Now that's great as an availability number, but when you combine them, all the aggregate failures that would have happened throughout that year, you actually will end up with 3 nines of availability for your overall service. And that's somewhere in the ballpark of between 8 and 9 hours a year, a big difference. And so to address this, Netflix defined this concept of critical microservices, the ones that are necessary to have basic functionality work. Can the customer load the app, browse and find something to watch? It might just be a list of the most popular movies, hit play and have it actually work. And so we've taken this approach and identified those services as a group and then created fit recipes that essentially blacklist all of the other services that are not critical. And this way we can actually test this out, and we have tested this for short periods of time in production to make sure that the service actually functions when all those dependencies go away. So this is a much simpler approach to trying to do all of the point-to-point interactions and has actually been very successful for Netflix in finding critical errors. So let's now talk about client libraries, shifting gears completely. When we first started moving to the cloud, we had some very heated discussions about client libraries. There were a bunch of folks who had done great work from Yahoo, who had come to Netflix, who were espousing the model of bare bones REST. Just call the service, don't create any client libraries, don't deal with all of that, just go bare bones. And yet at the same time, there are really compelling arguments for building client libraries. If I have common logic and common access patterns for calling my service, and I've got 20 or 30 different dependencies, do I really want every single one of those teams writing the same code or slightly different code over and over again? Or do we want to simply consolidate that down into common business logic and common access patterns? And this was so compelling that this is actually what we did. Now the big challenge here is that this is a slippery slope back towards having a new kind of monolith where now our API gateway in this case, which might be hitting 100 services, is now running a lot of code in process that they didn't write. This takes us all the way back to 2000, running lots of code in the same common code base. It's a lot like a parasitic infection, if you really think about it. This little nasty thing here is not the size of Godzilla. It's not going to take down Tokyo, but it will infest your intestines. It'll attach to your blood vessels and drink your blood like a vampire. This is called a hookworm, and a full-blown infestation can actually lead to pretty severe anemia and make you weak. And likewise, client libraries can do all kinds of things that you have no knowledge of that might also weaken your service. They might consume more heap than you expect. They might have logical defects that cause failures within your application. And they might have transitive dependencies that pull in other libraries that conflict in terms of versions and break your builds. And all of this has happened, especially with the API team, because they're consuming so many libraries from so many teams. And there's no cut and dry answer here. There's been a lot of discussion about this. It's been somewhat controversial even over the last year or so. The general consensus has been, though, to try to simplify those libraries. There's not a desire to move all the way to that bare bones REST model. But there is a desire to limit the amount of logic and heap consumption happening there. And you want to make sure that people have the ability to make smart, thoughtful decisions on a case-by-case basis. So we'll see how this all unfolds. This is sort of an ongoing conversation. And mostly I'm bringing up here so that all of you can be sort of thoughtful about these trade-offs and understand that.